Up next is a medium problem, reorganize a string. And basically this is what it's saying. You get an input string and your job is to arrange it in such a way that no two characters of the same characters are side by side. So in this case, A should not be side by side with A. So, and this is one way to do it, and another way to do that. So you shouldn't have like a character, the same character following itself in the sequence of the array. That's basically what this question is asking you to do. And so you have this, and then there are other valid answers. And if there is no way to do it in such a, to rearrange the characters in a way that the same character doesn't follow itself, then you just return an empty string. That's all there is to it. So any possible valid arrangement, any possible one, right? The naive approach is very complex. N factorial times n, yo. So this is what the solution to the problem looks like, the optimal solution. First of all, you want to create a frequency map of the individual characters in your input array. So you say B occurs twice, N occurs twice, C occurs once. And then you want to put those in a maximum heap, as you can see here, based on their frequency counts. And you pop, this is what the algorithm is going to look like. You take the first thing out of there, that's B, you add it to the result array, and you hold on to it for a second, right? Now it's 1, so it becomes smaller. Smaller is no longer on the top of the maximum heap. It gets pushed down and the N goes up there. And then you take N, you put it in there. They're all equal. However, when you take something out of here, you want to always pop it. You're going to put it back in the heap, but first you pop it so that something else goes on top and you don't have a character repeating itself. That's a key, a cornerstone of this solution. So when you take N out, there's still N in the heap and it still belongs there. However, you take it out so that B, something else, B or C, whatever, can be up there. And you pop that, put that in there, and then you put the N that was supposed to be at the top of the heap back on the heap. And I'll show you this in code, where this happens in the code. And you just keep doing that, popping and adding till you're done. And then you have this format. And because the heap is empty and there's nothing else to put back into the heap, you say you're done with the algorithm. So let's take it back from the top and look at code while we step through things. So first of all, you want to create a frequency map of the characters in your string, in the input string. That's what this is doing there. It's basically saying, oh, if you've seen this string before, just add 1 to the frequency. Otherwise, initialize it to 1. That's all this does. Then this is our maximum heap that stores our most frequent characters. Then you want to store each character and its frequency in the heap, and the heap property is going to be maintained based on the frequency count, which is, so you have the character, then you have the character counter. This gives us the frequency of the character, and we put it into the heap. Next, this is our bucket. Previous is our bucket, is the most recent thing that we've added to the result array is what previous is going to be, basically. So it's going to be one of the things we've removed from the frequency character tuples we've removed from the maximum heap. That's what you see over here. And result is the string that we're going to be concatenating and at the end of the day return, represented by this green bar right here. Hope that's clear. Moving on. Again, this is a medium problem, so you might have to look at it more than once, and that's okay. So while there is something in the heap, while heap.size is something truthy, or we have something that we've recently popped from the heap that still appears, right? That still has maybe a frequency of at least 1. That's what previous represents. Do this, right? This is the meat. This is what does all the heavy lifting for us. Now, I'm going to want you to ignore this for a second. Ignore this if statement for a second, but come over here with me. So we take the first thing from the heap, store it as element. The first element is the counts. The second element is the character. So the count and the character. And we append the results to the character to the result and decrement the count by 1. Okay? Because now it appears less, right? We've taken one instance of that character out of the equation, so it appears less. Now in this first pass, previous is still null, right? Imagine that previous is still null in this first pass. However, we have appended b, for instance, over here, and decremented its instance by 1. It was 2, there were 2 counts, now there's only 1 count. Now, because we've not set previous is still null, right? Imagine that previous is still null, so nothing here executes. So we can ignore this for once, for now. And we can ignore this first statement I mentioned because previous is still null here, remember. So this is not going to execute. So what do? Count is not equal to 0 even after being decremented. So previous is going to store the updated count and the character. So in this case, it would have held B1 and 1 and B, basically, is what previous would be. And now we're done evaluating B, because in this current initial state that we've worked with, B was popped, right? It was popped from the heap. Keep that in mind. Now we go again. Now we have something previous, but the size is not 0, right? The size of our heap is not 0, right? We still have these 2 in the heap. And so we take n out of it, n and its count decremented, add it to the result. We now get bn, right? Now previous is not null. Aha. So previous was b and 1, remember? So we're going to put it in there in the heap. So it's going to look like this, right? Put it in the heap and then set it to null. And then because n still has another instance, we update previous like that. So it's very important that whatever was popped before gets added in the second pass, right? In the second iteration of this while loop. And we basically do that to the end. Now, that handles everything except where we have a case where there's no possible way to arrange the characters in a way that the same character doesn't follow itself. That's what this handles. So if you have something that's previous and you have nothing left in the heap, right? To create result with, just return an empty string, because there's no way to reorder the string so that the same character doesn't appear side by side. Then you return a result when all this is done, when previous is null and the size is also falsy. When previous and the size are falsy, just come out down here and return your result, and c'est fini, you're done. The while loop is doing all the heavy lifting. And again, it's a medium problem, so you might need to look a bit harder at it to figure it out. Now, the time complexity is interesting. It's worth reading this. So you have to loop through the whole array at least once. So, and in the worst case, every popped element may be pushed back onto the heap. So when you pop an element from the heap, you might end up having to put back every single thing into the heap again, right? That's if everything occurs more than once. Every character occurs more than once, at least more than once throughout the whole thing. So we do that until we consider all characters in a string. So that runs O of n times, where n is the number of characters in the string. Now the worst case of the push operation is a heap operation, so it's O log of c, where c is the number of distinct characters in the string. Therefore, the time complexity is n, so you multiply those, n times log of c. Now, the upper bound of c, this is what's interesting about the time complexity. The upper bound is the size of the alphabet. You cannot have more than 26 elements in the heap because there are only 26 letters in the English alphabet. So the log c term is a constant, 26. So how do we deal with constants in time complexity? We drop them. So we just have O of n. Look at that, an O of n algorithm. Love it. And now it's a similar case because of the maximum number of alphabets in the English language. We have two data structures: a hash map, that's a frequency counter, and a heap. The hash map stores the frequency of characters in a string. The heap finds the desired string. both store lowercase alphabets, the maximum capacity of each data structure is 26, a fixed number, a constant. And so the space complexity is O of 1, because you cannot have more than 26 characters in the English alphabet. And that's all there is to this problem. See you next time.